Hey everyone, Phil from Ember Prototypes here. Sorry if it's a bit loud in here. I'm running a bunch of other things on several of our printers, so I'll just try to speak up. Today's video is going to be a bit different. It's actually a lot of work, and I'm not sure how often I'll make videos like this, but I hope that it's interesting and I hope that it's educational. So some of you may know that we make and we sell an optical camera assisted XY calibration tool for multi-extruder 3D printers. And recently there's been a bit more interest from Prusa XL users, even though they have an automatic calibration routine. And for a long time now, I've always thought that optical calibration was superior to mechanical calibration. Now, obviously, I'm biased because we sell this product, but I do think that there are some pitfalls with mechanical calibration that people maybe aren't necessarily aware of. And it doesn't affect everybody, but when it happens, it can definitely affect users, and it's not very easy to tell or understand what is happening. So in today's video, I'm going to be comparing mechanical calibration to optical calibration, talking about some of the pitfalls associated with mechanical calibration, and hopefully this will shine some light on some issues that maybe a few of you have been having, and at least just be kind of educational. I will try to stay as unbiased as possible, but of course, again, we do sell an optical calibration tool, so please keep that in mind when you're watching this video. And before we start, I do just want to give a shout out to all the creators who gave me their permission to clip some of their great content in order for me to make this video. So thank you all. And of course, I'll put links to all their videos and content in the description below. So let's get started. This video is sponsored by JLCPCB. JLCPCB offers PCB design and manufacturing services, but what some people maybe don't know is that JLCPCB also provides 3D printing and CNC machining services, which I've personally used quite a bit, and we actually use to manufacture the enclosures for our camera calibration tool. Our enclosures are actually MJF printed from JLCPCB, and they actually offered the most competitive pricing out of basically any other service provider that we looked at. When we first launched the CXC, we began by manufacturing the enclosures in-house, just using our Formlabs printers, but soon got to the point where it was no longer efficient for us to do that. And so JLCPCB has been making our enclosures for us for quite some time now, and we've been really happy with the quality, the price, and the speed at which they 3D print stuff. So thank you, JLCPCB, for sponsoring this video. Okay, so what is XY offset calibration? On dual extruders, IDEX printers, or tool changers, you have multiple extruders that sometimes need to go to the exact same physical location on the printer. Because of manufacturing and assembly tolerances, if you tell tool head 1 to go to position XY and then you tell tool head 2 to go to the same location, they will not arrive at the same physical spot. To correct for this, we need to calibrate offsets relative to one of the tool heads, typically tool head 1 or tool head 0. These calibration values tell the printer how much to compensate for in order to perfectly align the extruders to arrive to the same location. The traditional way to calibrate for these offsets is to print a line pattern with all the extruders. The first extruder will print this line pattern normally, but the remaining extruders will print the line pattern, slightly increasing and then slightly decreasing in the X and Y position. The user is then required to look at these line patterns and determine which pair of lines match up the best. The pair of lines that match up the best then needs to be counted, and that number will then correspond to the X and Y offset that you need to apply to your other extruders. Not only is this time-consuming and an iterative process, but it can also be just kind of confusing for newcomers and also be very error-prone. Some newer printers on the market are starting to incorporate fully automatic offset calibration to avoid some of the issues that we mentioned earlier. The Prusa XL is one example,
where it uses a probe and load cells in the extruders to touch off at certain points and determine the center of the nozzle to calculate offsets for each of its tool heads. The Snapmaker J1 is also another printer that does something similar, but instead of mechanically calibrating, it uses electrical conductivity to touch off on a square copper pad and also determine the center of the nozzle. Another way to calibrate for XY offsets is to use an optical technique. This basically uses a camera to find the center of each nozzle orifice and calculates offsets that way. Here you can see our camera-assisted XY calibration tool, or CXC for short, viewing the center of the nozzle orifice and recording its absolute position. The second extruder is then moved to the same absolute position and manually adjusted in order to line up with the center of the crosshair. The absolute position of the second extruder, once it's been lined up, is then recorded into the software, and a simple calculation is done to generate the calibration values. This process can also be automated by using the camera and machine vision with OpenCV. Basically, this automatically finds the circles that represent the nozzle orifice and calibrates offsets for you. This can be done using open source versions of something called TAMV and is used on various tool changers like the Jubilee or the KB3D black box. There are also some forks of this working with Clipper tool changers like the MakerTech ProForge 4. The nice thing about using an optical technique is that it's printer agnostic and universal. Here are some examples of our CXC being used on a variety of printer brands and different types of printers, ranging from tool changers to dual extruders to IDEX 3D printers. If you're curious about learning more about our CXC, you can go to our product page and watch all the videos. So like I said before, obviously I'm a bit biased because we sell a product that does optical calibration, but again, I will try to be as unbiased and reasonable as possible when making comparisons between mechanical and optical calibration techniques. The first issue with mechanical calibration that we'll talk about is probably the most obvious one, and that's if your nozzles aren't clean. If you have any type of burnt or stuck filament to the nozzle, this is going to introduce error when you do a mechanical calibration. In the case of the Prusa XL that's purely mechanical, this might lead to incorrect offsets. In the case of the Snapmaker J1 that relies on electrical conductivity, this might mean a completely failed calibration routine, or in the worst case, the nozzle moving too far into the copper pad and potentially crashing and damaging it, thus permanently messing up with your auto calibration routines. Both of these results can be really frustrating and time consuming. One of the big reasons to have some kind of assisted calibration routine is to avoid the iterative, time-consuming, and subjective nature of the traditional line pattern calibration technique. If your auto calibration routine has chances for failure that could potentially go unnoticed, this can lead to even more hours wasted than if you had done it the old-fashioned way. The easiest way to ensure that this doesn't happen is to simply heat up your nozzles and brush them thoroughly and then inspect them afterwards to make sure that there's no more residue or filament stuck on the nozzle. However, speaking from experience, I've definitely attempted to clean a nozzle before, only to find out once we use our optical technique that there's actually still filament stuck on the nozzle. So the nice thing about an optical calibration technique is that it essentially checks the cleanliness of your nozzle for free. Once you set up the optical calibration, you can tell immediately whether the nozzle is clean or it isn't. If you can't see the nozzle orifice, then it automatically tells you that you need to clean the nozzle and try again. Another problem with mechanical calibration is that it touches off on the outside of the nozzle in order to calculate the theoretical center. This theoretical center should be where the central orifice of the nozzle is located. However, because of manufacturing tolerances, this isn't always the case, and this is something that's called concentricity. Basically, if the central orifice is not concentric to the outside of the nozzle, then if you are trying to calculate the center of the orifice based on the outside of the nozzle, you're always going to end up with some kind of error. Lost in Tech recently released a really cool video that showed a lot of very detailed microscope images of nozzle orifices. In this video, you could see that some of the higher end nozzles, like the Prusa nozzles and the E3D nozzles, had very well machined center holes that were concentric to the outside of the nozzle. However, in his video, you could also see some nozzles that were very poorly machined and definitely did not have good concentricity. These nozzles, if using a mechanical calibration routine, will always give you an incorrect offset value. This video was really cool for various reasons, so I'll leave a link in the description below, and I highly encourage that you go and watch it. One of the reasons why you see these concentricity errors is because when these nozzles are manufactured, they're typically CNC'd on a lathe. This video from CNC Kitchen gives a good visualization of how these concentricity errors happen. Because the stroba is sticking out so much, and because it's very thin and long, once it hits the face of the nozzle, it starts to wander, and this wandering can lead to an offset error and an error in concentricity. Again, the nice thing about optical calibration is that you are only finding the center of the orifice. The geometry of the outside of the nozzle is irrelevant. In this example you see here, I'm actually calibrating a really old nozzle on my Raise 3D E2, and you can actually see how worn out this nozzle is, but most importantly, how not concentric it is to the outside of the nozzle. If you were using mechanical calibration on a nozzle like this, you would always get a bit of an error with your offset calibration. So you might be wondering, can you just QC for concentricity and just make sure your manufacturer gets it right? Well, you can, but it'll really cost you. So in the engineering and manufacturing world, there's something called GD&T. GD&T basically stands for geometric dimensioning and tolerancing. And this is essentially how engineers create drawings in order for manufacturers to make their parts and to ensure good quality. You can specify a call-out for concentricity in your drawings, and by doing so, the manufacturer should make sure that they hit your concentricity values. But there are several reasons why this probably doesn't happen. Number one is that tool changers and IDEX printers have only recently started to become more affordable and more accessible. So it's highly unlikely that people are actually calling out concentricity values on their nozzles when they're manufacturing them, because this hasn't been required in the past. Number two is that auto calibration is also fairly new. Number three, which is probably the most important, is that anytime you specify some kind of tight tolerance, it increases cost. It increases cost because it requires the manufacturer to use sophisticated techniques like CMM measuring machines to check and to qualify that they're actually hitting the targets that you specified in the drawing. I've also had some people ask me and also compare mechanical auto calibration techniques to CNC tool finding, edge finding, or tool setting. While these sound similar on paper, the big difference is that CNC machines are built much more rigid and much more precise than 3D printers. The amount of runout that you see on a spindle or a tool is significantly smaller than any type of precision or misalignment that you see on a 3D printer. A CNC machine is also a lot more rigid and thus less susceptible to damage and misalignment if there are any crashes. An example of angular misalignment causing problems for auto calibration can be seen here. This is a picture that I found on the Snapmaker J1 Facebook group a long time ago. You can see that the right extruder has a significant angular misalignment. The left extruder seems pretty straight, pretty square, but the right one is not. In another hilariously extreme example, you can see a very bent Bamboo Lab hot end. Because hot end designs inherently have an extremely thin and extremely weak point at the heat break, hot ends are very susceptible to damage and angular misalignment if they're bumped, knocked, or crashed. This is not the case on a CNC machine, which is meant to be extremely rigid and handle very high radial and axial cutting forces. To demonstrate the effect that angular misalignment can have on mechanical calibration, I've mocked up a demonstration where the hot end has an angular misalignment of around 2 degrees, which seems somewhat realistic. So knowing that mechanical calibration will touch off on the left and the right side of the nozzle, if your hot end assembly has some angular misalignment, in this case 2 degrees, what ends up happening is that the mechanical calibration routine will find what it thinks is the center of the nozzle, but it actually isn't, because there's this angular misalignment or angular error. What this essentially comes down to is the fact that for around a 2 degree misalignment, your mechanical calibration could have up to 0.1 millimeter offset error. And again, this is one of those situations where it doesn't matter how many times you run the mechanical calibration, it will always have an error with your offset. Similar to physical damage causing angular misalignment, physical damage can also affect wear and tear on the mechanical probe or on a conductive pad. This image, also taken from the Snapmaker J1 Facebook group a while ago, shows this exact phenomenon happening. Now, the issue here is that because this pad is asymmetrically damaged, it's always going to now give you incorrect offset values. Okay, so I've harped on mechanical calibration for a while now, but what are some advantages? Well, it does actually have some significant advantages. It's a lot cheaper and easier to integrate into existing 3D printers, and it's also a lot easier to automate. It doesn't require a significant amount of extra hardware or computational power, and the entire calibration process can be easily written into firmware. Automated optical calibration, on the other hand, requires some extra hardware and also requires significantly more computational power. Now, having said that, in my personal opinion, doing an optical manually assisted calibration is easy enough, fast enough, and accurate enough to not really need or warrant a full auto calibration. In fact, if you mount an optical system into your 3D printer and create macros to go to that specific location and bring the tool heads up directly over above the camera, the calibration process can literally take a minute. The other significant advantage that mechanical calibration has over optical is that you get all axes for free. And what I mean by that is you can automatically calibrate for XY offsets, but also for Z offsets. I do think that a well-implemented mechanical calibration routine can work, and work quite well. If you use high-quality nozzles that are machined with high-end machines at good manufacturers, and if your assembly and QC process is very good, and the implementation of your calibration is very good, I think mechanical calibration can be great. And it's amazing to see improvements in offset calibration for multi-head printers, because let's be honest, nobody likes the traditional line pattern technique. It's the absolute worst. At the same time, I do think that optical calibration does have some advantages, even if it's not fully automated. And I do think that automated mechanical calibration on tool changers is still so new that we have yet to really see some of the issues that I've talked about in this video. Prusa does a really good job of assembling, QCing, and testing all their machines before they go out. But at the same time, I don't think that the tool changers have been in the field long enough for people to start discovering problems like this. Once people start modifying their machines, changing out nozzles, crashing their machines, using third-party nozzles, some of these issues with offset calibration might start to arise. But I don't think that this will be a super prevalent issue. I think that some individuals might just get unlucky and encounter situations where their offsets are off, and no matter what they do, their calibration results aren't accurate. And for those individuals, the reason is probably one of the several that we've talked about today. And hopefully for you, the manufacturer can fix the issue, or you could try optical calibration, and hopefully that will solve your issues.
Okay, so I hope that was interesting, educational, and I think I did a decent job of staying as unbiased as I possibly can. Again, I don't think that this is a big problem, especially with higher quality companies like Prusa that have good QC, good manufacturing practices, and also just good implementation of calibration. But I do think that it's still a bit early to tell and to really start to see some of these issues crop up. So anyways, let me know what you think in the comments down below. Like, subscribe, and as always, thanks for watching.